Hi friends, so this we are into the fourth week of the topic prognostics and health management, a systems approach. Um, and in previous lectures, we introduced this topic that is PHM, a systems approach. And then we, second lecture, we took something like probabilistic and common notions, AI, ML, um, and of course, third lecture was dedicated to probabilistic methods. Because you know the importance of probabilistic method is that it is a part of prognostics and health management, as well as it is part of the probabilistic risk assessment, and that in turn is part of risk-based engineering and risk-conscious operation management system. So we have seen all these things. I have a book on this risk-based engineering 2018 that I have written, and along with Professor Michael G. Pett at University of Maryland, and risk-conscious operation management I have published in 2023. So that backup for statistical processes and risk assessment will be available there. And I think if you do that, probably your foundation will become more robust to handle the subsequent topics also. So today's topic is sensors and data acquisition system. We are talking about prognostics and health management. So sensors and data acquisition system is central to tap the symptom or precursor parameters and then feed it to an AI algorithm. So the importance of this particular topic is this, that a sensor and data acquisition system should be well designed and should be optimized such that we get a quality signal, and if the quality signal we get, then the diagnostics, prognostics, those parts they become much easier. So today in the first lecture, I will introduce the sensors and data acquisition system. It has got a little bit of more qualitative component, and then I have connected to two very important aspects of complex engineering system, that is PHM based on the already available parameters in the control room of a plant. That means that process parameter, safety parameter, can we use this signal and can I develop a PHM for certain components. Again, they will be acting like a precursor to even the precursor signals, like before a component degrade, its performance start manifesting into the process parameter quite often, okay, not always. And then second part is we are having one important parameter called common cause failure. In fact, it is more important in electronics because there are many sources of common cause failure. So I am trying to give a systems approach for PHM because that is what we should do at the plant level. Of course, for a particular component it is good, but then we have to think about a plant also, because finally we are talking about a maintenance strategy which is more or less time based preventive maintenance or condition based. So condition based maintenance we are extending to prognostics and health management. So it is highly relevant to any complex engineering system. So first we will see the introduction in this lecture the way it has been shown here, and then second we will see sensor specifications and applications. Of course, we are not going into the details of this thing, but from this week, whatever information you will be given, I am sure you will find pretty updated about how to go for sensor selection and what kind of format we should use, which are the most important specifications which directly impact our signal quality, and which are the things, other things with which we can manage. And then the third is data acquisition system, because sensor onwards, then a data acquisition system is concerned. Of course, there is a transducer in between, whether it is a part of data acquisition system or a part of sensor, but it is required because we have to convert any signal, pneumatic signal or hydraulic signal or any degradation mechanism information that is coming in, we have to convert into electrical system. So transducer are very important. Transducer are even sometimes transmitter when we talk in terms of process language parlance. And then data acquisition system in PHM. What are the specific things about data acquisition system in PHM that will be, and then sensor system for PHM of electronics. In fact, when we talk about the PHM system for electronics, the environmental parameters, they require very high attention in terms of monitoring and maintaining the parameter to the prescribed limits. Let us say if I have to maintain a ground benign environment in a place or a control room or instrumentation room, if I have to maintain the GB condition, ground benign condition, that means I have to have 22 degrees centigrade temperature and 50%, 55% humidity. So we have to maintain, otherwise the electronic system might not perform the way it is, it was expected actually. So for PHM there is a environment has a special attention, then sensor system, attributes and prognostics. Okay. And then as I mentioned earlier, there are certain aspects I am focusing on this, common cause failure number 1, and PHM for process system, using process system. In fact, you will see over a period of time during my presentation, you will feel that I am going overboard to say that before we go for PHM, let us use the plant existing parameters. That means no new instrumentation. You use those parameters, come to a stage of condition based monitoring and then prognostics. That will give a lot of lesson for the kind of system that we need to foresee in the future control rooms. Okay. So if I have to talk about basic health management aspects, the first argument which I am trying to argue is that process and electronics system should be taken at advanced stages of the plant, and that will help in validating. So use already available sensors and DAQ, okay, and then new sensor system for PHM that fit into existing plant. Okay. So in spite of this, in fact it can be a parallel activity also for some SSC, system structures and component. We can have a independent system which we are starting afresh also. Change in process and electronic instrumentation. PHM involves a lot of new electronics and data acquisition system. It helps us if we use this information and assess the gap area that is available, because PHM is a lineup where we have a mechanical component, electrical component, electronic component, it could be chemical reactor also. So, and from there sensor, and then electronic follows, and then the advanced AI/ML algorithm. So we are starting from something very traditional system, and we are going towards the most advanced like AI/ML application, and that too in real time environment. So it is expected that they will perform, they will meet our aspiration. And then yes, that requires an optimization. That is what the point is. And inventory of logistic, critical, sensor, and this thing has to be optimized in the sense that we have a priori idea on return on investment. The early we get that kind of benefit study like risk, reliability, safety, and then return on investment. So the more we can convince to the management that what should be our next, whether it is PHM or remain at condition monitoring or remain even traditional. So that depends on what kind of output, and once PHM opportunity has been given, we should use it and very sensibly use in the complex engineering system where impacts are very high actually. So with this having discussed, then then certain more aspects which are required. Um, Whether we are trying for PHM for a new plant, it is much easier to apply a PHM if you have algorithm with us. But then if it is a operating plant PHM, then we have to have a different because operating plant will have some advantages also, and will have some limitation or constraint also. Like in the existing system, we have to plug in our PHM components, and not only that, it should be free from any interference. It staff should be trained. All those issues will come, and then if we look at from this particular factor. And we should not forget one more thing: PHM doesn't work in isolation. There is a human factor component. Day-to-day maintenance things will be done on the system. So, it should be done effectively, well, so that we are getting the optimized output, and expectations are fulfilled actually. So then if I do that, then what are the sensor requirement? Again, I come back to my first thing. If it is a small upgrade, I have got a PHM system for a new system which is forming part of the plant, and I want to have PHM for that. That is one thing. But if it is a already operating plant like this one itself, and then we want to change the strategy from previous maintenance approaches to the PHM. Of course, all the system cannot be done. It will be done in a phased manner. But then we have to cater to all the operating plant requirement, some upgrades, some modification, and that's how. But then if it is for the new design, let us say the unit itself can be having an embedded PHM component into the system, and then we can link it to the plant control room, and we can have a these systems, the way we commission a process and electronic systems, these systems are also commissioned, and we have a thing. And then operations management. Therein the maintenance management is very critical component. At the same time, the operation management, day-to-day operation. Actually, when I say operations, the maintenance management operation, it is together they are called operation and maintenance, O&M. So maybe if I use the word O&M, it can be operation, because maintenance cannot be seen in isolation. The operation team and maintenance team, they work together to ensure that the plant is operating smoothly. In fact, if I talk about the plant availability, the maintenance role becomes very important, because the designated equipments, the critical equipment, they should be performing well to get the good availability factor from the plant, and that good availability factor only will deliver the output, whatever output, whether if it is an energy system, it is a power production, if it is depending on the product, there are different output. So maintenance things and operations ensure that the plant is maintained safe, and then safe, reliable, okay, without much interruptions. And then we have validation and verification offline, online. So you can imagine when some upgrades we are doing it, you have to go in parallel, you have to do that. When it is operating plant, you have to integrate all these things and do validation, verification. But if it is a new design, you can have some freedom instead of constraint the way it was happening in the operating plant, and maintenance management and all. So this is how it is. And then once validation verification is done, then probably a sort of a 1 year, 2 year feedback, so that is there, and then that will give us a confidence how well the new strategy is working. Now let us see overall structure of the data acquisition system at component level, how it is implemented. This figure I have made because in many plants we have used amplifier signal processing. So I have taken the you can say salient characteristic of operating plant and new plant, and I have tried to show as much detail as possible, particularly for the purpose of implementing prognostics and health management. So let us say we are monitoring three here SSC. I have given the abbreviation for this SSC. system structures and component. I, J and K, there are three structures, component or system, whatever you may like to think, and then sensors are there. So obviously when we are monitoring three, there will be three sensors also, but I am explaining through one SSCJ and one sensor, and so this form the part of the plant. Okay. Then we come to this transducer. Transducer can be sometimes part of the sensor or it can be independent unit. So transducer means that will convert these signals in whatever form it is, stress, strain, maybe some process parameter. So mechanical or the thermohydraulic quantities are converted through the sensor. For coming from the sensor, it is converted from the mechanical or thermohydraulic to electrical signals, voltage, current, and all you might like to think. And then it is fed to the signal conditioning module. Why? Because what kind of lineup, what are the voltage current they are coming here, and what is the compatibility with the rest of the system here, and what is the best accuracy that will get for a particular signal. All those things are optimized here, and then a signal conditioning module is incorporated into the line of prognostics and health management, DAQ. And then we have here, so once I use the signal conditioning, then next stage is analog to digital converter. Now you can see here, so here now we converted the current or voltage signal into the digital signal 0, 1, 1, 0, that stream of this thing. And then we also have access to the analog system, because up to here, at this point, we had all this analog signal. So analog can be, this question becomes more pertinent when we are talking about the old plant, because big chunk of systems, they might be analog, and in some plant which are built let's say in a decade or so or more, they might have really got it transferred to digital system. So we have a converter, and here it's a multiplexer. Multiplexer is what? It basically can take more than one input. You know, if there is one input, then multiplexer is not required, and it can go further for data processing as our ML algorithm is. And this conversion is mostly required. It is better to keep one A to D card or A to D converter, because you know anytime this need might arise. So if we early we can make it a part of the our integrated circuit, it is good actually. And then finally it is fed to, from here onwards it becomes a AI/ML system. So we can say it is not distinctly separate system, because data pre-processing, feature extraction, pre-processing, noise reduction, sometimes some people they might do it here itself, or you know, feature extraction. This is basically statistical. Here also there is a huge component of statistical approaches or classification algorithm and all that. And then finally it is fed to artificial intelligence and machine learning for prediction of RUL. And of course, it goes into the plant operation and maintenance ecosystem, and applications are developed and it is used. So now here I will say one word, because this system has been explained in many places in this presentation. So I am taking that opportunity to present this system. Basic functions remain same, but something which I want to emphasize, it will be coming I think 3 to 4 times in the 5 lectures. So if you have understood and you know how data required, in fact the best strategy I tell to my student is, you try to build your own system, because this system is very expensive actually, 10 lakhs or 16 lakhs to or 20 lakhs to somewhere around, you know, even as small as 25,000, 50,000, but of course functionality are limited. But not only understanding, but can we have for our own system a dedicated module of data acquisition system? There is nothing like that actually. Okay, so so you know that in PHM we are trying to monitor the degradation. So here just I am talking about mostly mechanical system. What are the degradation systems that are monitored, and they require either periodic or continuous monitoring. Continuous monitoring definitely in all the cases is not possible, because you require a system something like, and particularly for passive systems, you know, I had discussed in my previous lecture, these kind concepts are not, PHM is not new. Earlier also it were there, they were used like coupons or condition based maintenance, or so in electronics some sort of a testing device, periodic testing device. Now they are coming, thanks to this digital electronics, they are coming in a very integrated form and the efficiency is much better. So if you start from corrosion, corrosion is a highly prevalent mechanism. Probably if we see cost, if you compare, it comes into billions of dollars, you know, at a level of a nation, you know. So it forms 3.34% of the gross domestic product, GDP. So this is the importance of having such an important topic with us, where we are monitoring the corrosion rate also, because the corrosion is basically it in mechanical parlance, it reduces the strength of the component and the pressure load carrying capacity, and which can be fatal, you know. So one thing is the replacement cost, the management cost, this itself is so high. And second thing, the loss that is happening when, let's say, some pipe rupture, carbon steel pipe, it ruptures because of corrosion, internal corrosion, and then we pay through heavily, and that's how it becomes such a big component. It is billions of dollars, US dollars, you know. Similarly, erosion is basically for applicable for this is for passive component mostly, and this is for this is basically for relatively moving parts in a machine. So erosion, that limits the life of the component, corrosion limits the life of the component, and then we have a wear phenomena. Okay, so let's say in bearing we would like to see a wear happening at the inner race, outer race. So those kind of thing we can, and that gets manifested into the rising temperature or vibration. So we are talking about the basic fundamental degradation mechanism only. Fracture, I would say, if we want to predict the fracture, lot of uncertainties are associated with the model itself is so complex. It has got so many lifetime loads, and then so basically it is what it is done in the plant is, there is something called in-service inspection, which is done to address the corrosion, fracture, this kind of issue, and then you try to predict the life and symptom. If any crack is there, then you will be able to know through a sensor. But you see, that also happens periodically. Let us say for each component it is a couple of years that turn comes, and the coverage is always in a question actually. So why not have a online system which can be using the secondary or third, like leak before break kind of phenomena. Why you allow fracture, leak before breaks, even a small sweating should be able to tell you, and that can happen only with the prognostics and health management logic. Fatigue, okay, so components, in fact, fatigue acquires a bigger dimension. Of course, it is a part of the mechanical things and all that, bridges and all, but it is equally relevant to electronics also, because solder joints are major contributor to the electronics failure, and that's where fatigue failure has been seen because of fatigue, not because of mechanical loading, it is because of thermal. In mechanical component it is mechanical loading. So but it acquires a high dimension when we talk about the solder joint. Sometimes it is for quality, sometimes delamination, there are so many things we will see as the presentation goes on. And cracking is a phenomena which is happening in cracking and delamination. These go together. At the outer surface, this phenomena occurs. You know, so delamination is considered to be one of the it happens at the one layer is piling out. So it is considered not good, especially in concrete and all. They are very important. And then embrittlement. Embrittlement is basically the material becomes brittle over a period of time. Like for you take the case of chemicals, they make the material brittle. Even nuclear component, the brittlement studies, especially for the life limiting component like reactor vessel and all that, these studies are done. So in short, what we have done is we have seen important degradation mechanism, and we at one point only we can indicate, the costs are very heavy, and that's why online monitoring is material degradation mechanism is required. Okay. So now we go to the next key, how we can take the things further. Okay. Let's say we have environment, and what measurements or symptoms or precursor to be monitored, and what is the significance, So let us say, and what is the requirement for PHM? So let us say PHM, it requires to monitor the environment other than the degradation specifically, and then environment altogether. I'll tell you there is a bigger dimension of environment because it induces common cause failures also. So what we are supposed to monitor in environment, it should be temperature, humidity, dust load, fog, gravity. So these are the things we should monitor because they impact a lot the operational components. Okay, and mainly it reflects on common cause failure. It doesn't mean that the plants don't have any defense for common cause failure. There are number of defenses are built into the common cause failure, but if you look at the safety assessment and all that, still common cause failure requires a special evaluation because the common cause failure has potential to kill the redundancy, maybe diversity not to that extent, but there are some common cause mechanisms like seismic loads. So seismic loads, they can couple between one safety system to another safety system performing the same function. So that is the importance of environment. Material, we know that stress, strain, corrosion, they are very important. They have to monitor spallation, pitting. Okay, they are the first sign of spallation and pitting. They are the first sign of aging and material degradation actually. Then electrical, yeah, they have little different current, voltage, capacitance, impedance. If it is DC, AC, that way you can take. And all the electrical equipment, all electronic equipment, how they degrade, increase in resistance because of some oxide formation on some contact, voltage reduction, current, fluctuating, capacitance, in fact, these are the parameters they are used to monitor some of the PHM devices also, impedance, capacitance. So equivalent series resistance in a capacitor, if it reduces, that means capacitor is degrading. Then mechanical, you have stress strength. It was at material level. Now mechanical level, stress strength same, because we are talking about material, microscopic and nanoscopic properties. In fact, earlier we used to get satisfied with microscopic thing. Now we have gone to the nano, 10⁻⁹. Okay, and that's how we can see the crystal structure there, what is happening at the material level to the nano range, and then we try to understand the kind of failure mechanism, degradation that is going to happen, wear, density, fracture and all, they are specific to mechanical degradation. And then chemical, the corrosion, carbonation, spallation, pH, conductive. pH is a the neutral water has a pH of 7, and above that it is acidic, and below that it is acidic, that 3, 4, 5 they are acidic, and 9, 10, 11 up to 12, 14 it goes. So then it is base. So that is, and they degrade the component very fast actually, and conductivity, isotopic purity, turbidity. Okay. So you have on pH acidity or alkalinity. Okay. So and acidity domain is 0 to 7, and then here 7 to 14 is alkalinity, and they are the biggest parameter for inducing corrosion into the system. Nuclear parameter, you have neutron density, embrittlement, radiation type and levels, monitoring and all that. So they are specific to. And then human. This is one of the takeaway from this lecture, that breathing, human in open domain you will find, though it may not be fully correct, but then the 50% to 90% accident they happen because of human. And if we exclude human from our any walk of life, then probably the treatment is not complete. So here I am including, in fact, in reliability now there is a complete field, human reliability, which is being developed. Only problem is the state of art is such that we are getting with results with higher uncertainty. Like normally it is accepted, error factor of 3 and all that, but here it goes to 5. But work is already going on, and some method I'll develop, I have developed, and we'll talk about it. Then electroencephalography is one. This machine, they will tell you alpha, beta, gamma wave, what you are thinking when your mind at peace, because you know that you do mistake when you are in under stress condition. So what are those conditions? They are defined by this waveform. Okay. So human health is very important. In this lecture, overall prognostics, human prognostics is the thing which how much time we'll be able to devote for it, I'm not sure, but I'll be touching upon this often actually. Okay. So now then resources, the electrical parameters and all SSC monitoring. So we have resources. It must be or recognize that the PHM is a resource intensive option. That means optimization should form part of it. So R&D is required here. Okay, because 20% R&D will be there when you want to implement PHM. Even if you do for routine jobs, probably some sort of a component which will come for research and development. So then operating ecosystem, as I mentioned, it has to be addressed. If PHM is not addressing the operating system, then life cycle loads you will not be able to monitor. Then you will not be able to see why your component has failed earlier to the specification whatever we got, or why it is not failing otherwise around also. So operating environment is very, and most important thing is return on success of PHM will be decided by return on investment. We invest in this technology and how much benefits we are drawing actually. And then there are maintenance aspect. When we implement PHM, there are overall organizational changes that you have to do, especially in maintenance and operation ecosystem, that might start from procurement, documentation, training and all that. So that has to be seen, and of course expertise should be available. Now it can be done based on what we have discussed, something like systems approach and all, and process system. So it can be, PHM can be implemented. First phase should be understanding, should give us time. So identification, prioritization. Which component require the highest, they are highest ranking and they require. So let initial 20% component, and I think you will be assured that 80% of the issues that you have resolved by addressing 20% component. Phase 2 is consider processing electronics and this kind of system, because it is easier to implement PHM on them. And of course, with the environment thing, you have common cause failure. You must understand that sometimes human error can become a common cause failure. If I had 3 system parallel redundancy was there and some calibration checks were done wrong, or some let's talk about some pump or bearing and all, the same contaminated oil got added into the 3 bearings, we compromise with the redundancy. So human factor is again important for PHM also. The wrong algorithm not working in some domain can give us not very wrong results actually. The remaining critical location of SSC can be induced in the, and then once we do that important thing, then we can go into the real, depending on our excitement or our impression about PHM and all that. So this is what, and then at the end of the time, it is RUL, remaining useful life measurement, or remaining useful time available. This is something new in the context of process instrumentation that I am not talking about. And now there are also aspects like project organization and management. They are sort of comes with any technology when you are changing that, whether PHM is going for as part of upgradation, process system for PHM, administration, and then organizational changes what we have to do. Probably we can see revelation, last corrective action and all. So friends, we are concluding 4th week's first presentation, and the overview is like this. We got introduced to the PHM, of course, we have been talking about, but we got introduced to sensor and data acquisition system. Only we have done a sort of a overview. Detailed things we will be discussing later on. And a view of existing and projected PHM system, what is going to be and what are the requirements, and we have given our own thought, and especially you can say take away like common cause failure, then human factor consideration. Okay, so this is and then of course in operating plant, how we can demonstrate the applicability of a PHM system. And then before implementing PHM, we have to have a project report, and that project report will explain the power and advantages of this thing, and that's how. And then of course when we go at the plant level, a regulatory clearance is always required, because we will be touching, if suppose we are touching safety system, even in process system, if we touch it, if we are making any fundamental change in the plant, then we have to take regulatory approval, because it is going to become part of the safety document. And then validation verification strategy, and how we will maintain it and all, and how upgrades will be required to the existing maintenance system. So this is what we have this final comment from this week. These references are very important, because many of these references I have used from in this presentation, and there is one book on PET M, and he is my co-author in my book on risk-based engineering. So, so this is a prognostics and health management book, Wiley, 2018. Probably you have to have, if you have this book, there it will be advantage. And then there is a PHM standard. One is the NASA has got one physics of failure book, which explains PHM using physics of failure approach, and then about race, and there are so many books. And the most important thing is there is a PHM standard available. If you want to, you are serious getting into the PHM thing, you should buy this standard. It is from $100 to $150, and it is, I think, 20-25 page standard. One should have it. And then my book on prognostics and my papers are there in the open domain. You can download these papers. And yes, this will be adequate for this lecture, that is 4th week.